Hello and welcome to the third video in the A1 series. In this video I will just be introducing you to SUVAT and the meanings of those letters, and then we'll be catching up on practice questions from the good book, and in this video we'll be doing practice questions 1, 2, 3 and 4. Please enjoy. Thank you. Right, welcome back. This is video number 3 of hopefully many. Video number 3 today. We're going to briefly look at the equations of motion, which should all be familiar stuff to you, but I need to go over it because this is a course for everyone, not just a course for people doing IBDP. This is people interested in physics, and maybe they missed out on earlier stuff. So we can't do physics IBDP without doing this stuff and being very familiar with it. There are 5 letters, and together they spell SUVAT, and you've probably heard of SUVAT equations. You have to know what each of the letters represent, and then we are going to derive, either using words or graphs, the equations of motion. We are not going to be deriving using mathematics one of the equations of motion, because I don't do heavy math this early on in the course. Not going to happen. So S stands for displacement. That is the distance you have travelled in a straight line from where you started your journey to where you ended your journey. Let me just very briefly digress. Here is a flower. Here is a bee. The bee starts over here and flies around the flower. Buzz, 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 goes there, buzz, 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 and it ends back up just slightly below where it was. The distance travelled by the bee is the length of its convoluted journey. Maybe 25 metres. It maybe travelled 25 metres. And let's pretend that this whole thing, took 10 seconds. You could argue that the bee was travelling at an average speed of 2.5 meters per second, because it travelled 25 meters in 10 seconds. However, in physics terms, it left from this point here, and it came back to this point here, and the distance it actually travelled, let's say this displacement, that's called the displacement, of 1 meter. This is where it gets tricky, everybody, because from now on, we are defining velocity, not speed, but velocity, as the displacement divided by the time taken. So what was its velocity? Its average velocity over 10 seconds was 1 meter displaced divided by 10 seconds, 0.1 meter per second. So that means, just again, digression, 400-meter runners, they run round an oval track, don't they? They run round it. It's 400 meters. And world record people do that in around 40 seconds. So a world-class sprinter is travelling at an average speed of 10 meters per second, because they have travelled a distance of 400 meters in 40 seconds, 10 meters per second. What was their average velocity? Or what was their velocity? Their velocity was 0, because they started and finished at the same point. Their displacement was 0, and 0 divided by 40 seconds is 0. To which you say, well, that doesn't make any sense. Well, tough. Velocity is the displacement divided by the time. Now, usually the displacement will be the same as the distance travelled, but over the coming months you will see that that is often not the case, like in this sort of case. So you've got to be very careful. So S stands for displacement, and the units of displacement will always be generally meters. Meters. U and V are simple. They are initial or starting. Now, because we're doing grown-up physics now, we are talking velocity. Initial velocity. Final velocity. If I say speed, from now on, I have made a slip of the tongue. I really mean velocity. So S is displacement, U is initial velocity, V is final velocity, A is simple. It is acceleration, the change of velocity. And here is the single most important thing. For all of the equations of motion that we are going to do, they only work if the acceleration must be constant. If you are told the acceleration is changing, you cannot use any of these equations at all. They don't make any sense. Acceleration can be any number, but it must be constant. And so an acceleration would typically be plus 5 ms to the minus 2 or minus 2 ms to the minus 2. T, finally, obviously, is time, and we usually use seconds for time. You have got to know these 5. S, U, V, A, T. You can remember which is initial and which is final because initial, U, comes before V in the alphabet. U, V. Initial, final. Now here's how the game works, and it really is a game. In physics, they will give you some sort of weird question, and you will have to work out from this weird question 3 of these values. Because if I give you any 3, you will be able to use equations to work out a 4th one, and then, if need be, work out a 5th one. I have to give you 3 numbers for you to be able to work out everything else. A lot of kids go, I haven't been given 3 numbers. Well, sometimes it's hidden. So we're going to do an easy one first. We're going to do lots and lots of questions now. Okay, so now before we go on and do more of this stuff, I realise that we're getting ahead of ourselves with the book. You will be following along in the good book with your teacher, and I have realised that we have skipped over some practice questions in the book. Now, you will know that there are worked examples that you will have done because they give the worked example with the answers. That's for you to look at. But you will notice that there are no answers given in the book for the practice questions. So my job as part of this course is to cover every single practice question in this book and go through it in detail with you. Because if I don't do it, who's going to do it? Maybe your teacher. That's good. So I'm going to make a point of making sure that we do every single practice question. So here we are, practice question number 1, page 11, the very first practice question in the book. And it says, a boat travels east for 2.5 kilometres and then travels due north for 3.8 kilometres. Question A, part A, what is the distance travelled by the boat? Well, this is not high-level mathematics. It travelled 2.5 there, it travelled 3.8 there. They want the distance travelled by the boat, which is simply 2.5 plus 3.8, which is 6.3. If they had asked for the displacement of the boat, which is the next part, they're going to be asking you how far it is from there to there. So part A is the distance travelled by the boat, which is simply 2.5 plus 3.8, which is 6.3. Question B, the magnitude of the displacement of the boat. What does that mean? It basically means they went that way and then they went up. What is the distance from the start to the finish in a straight line? And that, everybody, is, drumroll, Pythagoras. So we're going to do 2.5 squared plus 3.8 squared equals, and then we're going to square root the whole thing. 4.548. So the answer is 4.55 kilometres. In fact, interestingly, they're giving it to you in 2 significant figures. So we should really be giving our answer to 2 significant figures. 4.55 kilometres. There's no sign on that because it is what the magnitude of the displacement. The distance from there to there is 4.55 kilometres. And then finally it says the bearing from north of the displacement of the boat. What does that mean? We haven't even talked about trig in your old page 11, and you've got a question here involving trig, but never mind. There's north. They want to know what the bearing from north is. They want to know what that angle is in degrees. What is that angle is what they're asking you. How can we work it out? The way I would work it out, because I'm simple, is I would look at this right angle triangle here. I would say that's 3.8, that's 2.5. This relationship between going up and going sideways, this is called a tangent. So I would do 3.8 divided by 2.5, and arctan it, and it would give me that angle. Take it away from 90, and I would get that angle. Obviously, you can just do it up there, but I'm not going to do that. You could do it the other way. No, do it that way. So here we go. Are we all happy that from here, that's the opposite, that's the adjacent, opposite over adjacent is tangent. So let's go. 3.8 divided by 2.5 equals 1.52. Shift tan 56.65 degrees is that number there, that angle there. I don't want that angle there, I want that angle there. Take it away from 90, or that minus 90, 33.3. We had to use a little bit of basic trigonometry there. I will probably have a session with you on trigonometry in the next few lessons. We'll just do a lesson on trig, just to go over the absolute basics to make sure that you're not one of those kids that comes into my classroom and goes, Sokotor, Sokotor. You have no idea how irritating that is to me. Without even understanding anything about triangles or trigonometry, they just go, Sokotor. Not doing that. Okay, welcome back. And before we do the next question, practice question 2, just a little bit on referencing these videos for everybody. I've just started this series of stuff, so I've got to come up with a plan for how we label them. I'm going to go with the book, the good book. We are currently doing the first section, section A, space, time and motion. And within the book, we are doing what they call topic A1. So the name of the video you are currently watching is topic A1 dot 003, because it's the third video in the series of the A1s. We are now going to do practice question 2, page 11 of A1. And the question is this. There is a minute hand of a wall clock. It is 15 centimeters long. Calculate to the nearest centimetre the distance travelled by the tip of the minute hand and the magnitude of its displacement from 12 o'clock, that's straight up, to the side at 12:15, and from 12 o'clock to 12:30. Let's do the first question. It wants to know the distance travelled by the tip and the magnitude of its displacement. The tip is travelling in a circle. Do you agree that from there to there, it's travelled 1/4 of a circumference? What is the circumference of a circle? The circumference of a circle is, all together now, come on everybody, 2 pi r. So if I put in here 15 centimetres, I will get the circumference all the way around. Let's do that anyway. Okay, so all we need to know is that it's 94.23 centimetres all the way around. We've done 1/4, so times it by 1/4, 23.56 centimetres is that distance travelled. We'll do distance travelled for the second one as well. Do you agree that going from there to there is a half circle? So it's half of this or twice that, times it up by 2. So it's 15 pi. So that is 47 centimetres to the nearest centimetre, and that is 24 centimetres to the nearest centimetre. 24 centimetres and 47 centimetres. Yes, I know that 47 isn't double of 24 because I'm taking each answer and rounding as they wanted it. The second part of the question is displacement. What they want to know is, in a straight line, what is the distance from there to there? Because the question says, read the question to you one more time, and the magnitude of its displacement from 12 to 12:50. The minute hand has gone from the hour to 15 past. The displacement is the distance in a straight line from there to there. What have we got here, everybody? A right-angled triangle. 15, 15. I have a right-angled triangle. 15 and 15. How do we work it out? It's the hypotenuse. 15 squared plus 15 squared equals square root answer 21.2 to the nearest centimetre, 21 centimetres. What is the displacement from here to here? Easy peasy, because it's simply 2 lots of 15, isn't it? Because it's 15 to there and 15 to there. So that answer is 30 centimetres. Everybody okay with that? Thank you. Okay, welcome back. We're going to do practice question 3, PQ3, which is on page 12 of the good book. And this is where it's all starting to get a bit harder. Two cyclists, A and M in the book, they go in different directions on a straight road. After 1 minute, A, who's travelling at 20 kilometres per hour, she's travelled for a minute, and she is now 580 metres from B. Determine the speed at which Matt, that person B down here, rides. This is quite hard. Number one, right, we are doing physics with Mr. Grunwell, and I am not going to have any of this old nonsense. Okay, we're going to sort our units out, and we're going to use one set of units for our calculations. There are other ways. I can hear other teachers go, oh, what you got to do by giving minutes and 16th of an hour and all that stuff. Not interested. We are going to convert everything to meters per second and meters. We're going to do that first. If I travel at 1 meter per second, and I travel for 1 hour, which is 3,600 seconds, I will travel 3.6 kilometers. 3.6 kilometers per hour is 1 meter per second. So to convert from kilometers an hour back into meters per second, I divide by 3.6. That hopefully is something you all know. 5.56 meters per second. Excellent. And this is 60 seconds. We are told that they are travelling 5.56 meters per second for 60 seconds. They have travelled a distance of 333.6 meters from the start. One more time. We convert kilometers per hour into meters per second. We multiply meters per second by the time we were given, 1 minute. So we know that she has travelled 333.6 meters. She is now 580 away from B. So take away the 580. We know this missing number is 246.4 meters. Okay, and what they want to know is what is the speed at which Matt rides. Speed, distance over time, 246.4 meters divided by 60 seconds tells me that they are travelling at 4. I'm not going to round on the calculator, 4.106667 blah 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 meters per second. Let's turn it back into kilometers per hour. Multiply by 3.6. Final answer, 14.8 meters per second. That's an interesting question because it involves conversions. One last time, go over this. Ready? You are told that A is travelling at 20 kilometers an hour. Divide by 3.6, turn it into meters per second. Times by the time they travelled, 60 seconds, 1 minute, to give the distance they travelled, 333.6 meters. At this point, they are 580 away from B. They've travelled 333.6 from the start. B must have travelled 246.4. 246.4 divided by 60 seconds gives them that speed. Multiply by 3.6, 14.8 kilometers per hour. Final answer. Any questions? Excellent. Okay, welcome back. We're now going to handle practice question 4, page 12. Again, they're throwing lots of different stuff at you, so let's spend some time and go through this. You are told speed of light is 3 times 10 to the 8 meters per second. That is correct. And that's the number you will use from now on. You are told that Sirius, a star, is 5.5 times 10 to the 5, which is 550,000 AUs. An AU is an astronomical unit. An astronomical unit is the average distance between our star, the Sun, and the Earth. And the average distance is called an astronomical unit. And because it fluctuates slightly during the year, because it's not a perfectly circular orbit, doesn't matter. Sometimes it's slightly more than that, sometimes it's a tiny bit less. We use this number. In English, what is this number? Forget all that. It's 150 million kilometers. Because that's how far it is from the Sun to the Earth, 150 million kilometers. That would be 150 times 10 to the 6 kilometers. And because a kilometer is 1,000 meters, to turn it into meters, you make that 9. And to turn this down into this format, it'd be 1.5 times 10 to the 11 meters. Are you okay with that? That's where it comes from. Okay. Let's explain what an astronomical unit is. They want us to work out the distance in light years. A light year is the distance travelled by light in a vacuum in 1 year. To work it out, we will multiply the number of seconds in a year by the distance you travel every second. So the speed, 3 times 10 to the 8 meters per second, multiplied by the number of seconds in a year. There are 60 seconds in a minute, and 60 minutes in an hour, and 24 hours in a day. So we are going to work out how far a light year is in meters. We are going to multiply the speed of light in meters per second by the number of seconds in a year. Now the good news is that we're only going to do this once because I'm going to expect you to remember these numbers in future. There are 60 seconds in a minute, and 60 minutes in an hour, and 24 hours in a day. How many days are there in a year? We are going to use 365 and a quarter. It's not exact. There will be a video where I'll be talking all about calendars and all this stuff, but at the moment we are going to use that. So, 31,557,600 seconds. I expect my students, when I ask them how many seconds in a year, to go, oh, I know, 31.56 million. How many seconds are there in a year? Answer, 31.56 million. If you use this in all your calculations, you will be fine. So all we have to do now is multiply 31.56 million by 3 times 10 to the 8 times 3 times 10 to the 8. And we get this number. Oh, I've got no room on the board. 9.47, rounded to, times 10 to the 15 meters. That's a number for you to remember. It's on your data sheet, I think, somewhere later on. The distance of a light year in meters is 9.47 times 10 to the 15. Or at least that's the number that I'm always using with kids when we do astronomy. 9.47 times 10 to the 15 meters. Okay, so the question was, how far is Sirius in light years? We're going to multiply the distance to Sirius by going that number multiplied by what an AU is, and then dividing it by that number. So 5.5 times 10 to the 5 multiplied by 1.5 times 10 to the 11 equals 8.25 times 10 to the 16 meters. That's a bigger number than that, so it's going to be more than 1. I'm going to divide this by that. Divide 9.47 times 10 to the 15. Answer, 8.7 LY, 8.7 light years. It's interesting that they've asked all these questions without explaining very much about any of this by the time you get to this book, at the time you got to this point. I hope that answers this PQ. Okay, so we've done the practice questions through to question number 4. Because of time constraints, we are now at the end of A1.003. Next time, in video A1.004, we will be going through the remaining practice questions, questions 5 to 11, and then we'll caught up with ourselves in the book, and we'll be able to start derivations graphically of Suvat equations. But we need to work our way through these rather painful practice questions next time. See you next time. Bye.